listen hang up and to Queen, I think the content is quite enough. And the speaking English to Queen and hang up, I think it's quite good enough for listening and yes, I think it's not clearly easy to follow, easy to listen to, and the content is quite enough for understand about the correlate relating to the electron configuration and periodic table. However, I would like to have some conclusions about this part of this section. And this is the content electron configuration here. Yes. Firstly, we have yes, we already stated about the Hans rule. Where is Hans rule? Yes. Yes, there is a electron configuration. Firstly, you need to remember that electron group fills the lowest energy state with the smallest value of n and l. Yes, and then fill the higher states until all electrons are in place. Yes, for example, you have hydrogen. So in the ground state, one electron in hydrogen will occupy the first state or the ground state. It is n equal to 1, L equal to 0, and ML equal to 0, MS equal to plus or minus a half. It depends on. Yes, and the helium, for example, you will have 2 electrons, and 2 electrons will have the different values of MS. Yes, only different in MS. If this atom is in ground state, you need to remember that it's in the ground state. Okay, so if the excited state is not this picture, it is excited state. It's very, very different from this. Yes, there is some picture about the ground state of the atom. And electron configuration. Hans rule. The Hans rule here, you need to remember about the ordering of electron in the orbital. For example, you can see Bohr here. Bohr have 1 electron in 2p subcell. So this 1 electron occupy the first orbital here. However, when you have carbon have 2 electrons in the 2p subcell. So in this case, 2 electrons are not in the same orbital, like this. It's in this form. It is this form. So every orbital will be occupied by the same orientation of spin electron before this orbital can be occupied by 2 electrons like this. So with each state of atom, so the number of orbitals have the same or have the singly electron in one orbital is maximum. So from this, you can see, for example, for Bohr, you can see that the quantum number S equal to a half. And for carbon, for example, here you can see that the quantum number S is equal to a half plus a half and equal to 1 here. So in this case, S maximum. And this in nitrogen, you can see that S in this equal to 3 multiplied with a half. So S in this case is also maximum. Yes, and then if you have one more electron in oxygen, so this electron will occupy by in this orbital. And in this case, you have two singly electron orbital and one double electron, one orbital here. Yes. And you can also see here that in 2p, so the Hans rule, the second point in Hans rule is L, the quantum number L is maximum. In this case, I already said that it is the corresponding to ML. So L maximum. So in this case, you can see if you have 2p, so L equal to 1. Okay, so you have ML here is 1, ML here is 0, and ML here is minus 1. So you can see that firstly, if you have one electron in ball, firstly, so if L max, so the electron in this case will occupy the first orbital. So that's L max. So in this case, it's occupied the L equal to 1 or ML equal to 1. So that's L in this case maximum. L in this case equal to L in this case equal to 1. Okay. So secondly, when you have two electrons in carbon, yes. So L in this case equal to 1 plus 0. Yes. And the third, L in this case equal to 1 plus 0 minus 1 here. Because you have three electrons in three orbitals. Three orbitals with the three different values of ML. Okay. So in this case, you also have the L max in this case equal to 1 plus 0 minus 1 and plus 1. So in this case, L equal to 1. Yes. So it is the configuration or obeys Hans rule of atom or natural atom. Yes, something you need to remember about this. And in the periodic table, you will have three, or you have some properties. And I think Hàn Ngọc and Tu Quyên already state quite full about this. And from this, you can have some properties like this. Yes, this is the full or the total picture of the periodic table Mendeleev. So in this, I think there is something. Yes, this you can see the total, and from this you can see the group in the column. So you have the name group. Yes, and in the row you have the periodic, the cycle here. So you can see this is a group one, yes, and group 2, yes. Yes, this is a group 3, and group 4, and group 5 here. Yes, and in this reason, you have the transition elements. Yes, it is a nguyên tố chuyển tiếp. Okay, so what is transition element? So you need to have some concept about transition element. The first properties of periodic table. Elements in the periodic table are arranged so that element in one column have similar chemical properties. So you need to remember this because we don't have many or much time to this. You remember that. For example, you remember that lithium or natrium, yes, natrium or kali or potassium and sodium. Yes, there are one electron in the outermost cell, so it's easy to take one electron from the neutral atom, and all atoms become positive ions. Okay, so it is the first properties. In one group, the element have the similar chemical properties. Yes, and the second properties of periodic table. In each row or in a period in a cycle, you will have the chain of ionization energy. Ionization energy in this case is the energy you need to supply into a neutral atom to take or to ionize or to take one electron from the outermost cell. An atom become an ion. Yes. In this case, you can see that for the first period and the second period here and the third period here and the fourth, yes, continuous. You can see that the ionization energy increase from the first element to the final element. The ionization energy increase. And in the next period, you can see the ionization energy increase too. The ionization energy increase too, and increase too. Yes. So you can have the second properties is the increase of ionization energy. Yes. And the third, it is the occupation of electron in some special subcell. For example, here you can see two special subcell here. It is 4S1 and 3D1. Yes, it is 4S and 3D. 4S and 3D. You can see that 2S can occupy or full occupy 2S2. However, 3D is empty or still empty or unoccupied. So 3DN and N can different from 10. So in this case, the arrangement or the occupied electron does not follow the principle. The lowest energy level to the highest or the smallest N and L values. So in this case, 4S are occupied firstly and then 3D. So in this case, it's very special. It's very special. And from this, you can have the first transition element range. The first transition element range. It is 4S2 and 3DN. Yes. And in this case, you already have the transition metal. You have transition metal here. Yes, they are all the metal, and it is a transition metal. Yes, however, this is not only for 4S and 3D. It can happen with, in this case, you can see 4D and 5S. In this case, 5S can be 5S2 or 5S1. However, 3D is unoccupied or 4D N and N different from 10. And you have the second element or transition element here. The second transition element here. This corresponds to 4D and 5S. Okay. And then you can see the special or the sum. Yes, the some series of transition element for example, the lanthanide area, for example, lanthanide area here, lanthanide areas, and you can see that it occurs with 4F and 5D, and the actinide series is a 5F and 6D. Yes, in this case, you can see that the outer subcell, does not or unoccupied, while the inner subcell occupied. Yes, in this case, you can see the lanthanide series here. The lanthanide series in this position in the periodic table, and the actinide in this position in periodic table. Yes, it contains a lot of elements or a lot of atoms. Yes, it's in this side or this side in the periodic table. Yes. There is some change in the periodic table that you need to remember, because the outer subcell are occupied. However, the inner subcell is not. It's happened because the energy of the subcell are the same or similar, or sometimes it's smaller with the outer subcell in energy. Yes, and spin orbit coupling in many electrons, so I already stated for you. And something relating to the spin orbit coupling and the yes. You can see here for the many electron atom. I'm sorry, for the periodic table. Do you have any question? I'm sorry. Do you have any question here?
Cho cô cho em hỏi một câu này.
Yes.
Em không hiểu vì sao nó không được viết là 3D4 3D44S2 mà nó lại viết thành 3D5 4S1 ạ. Cô giải thích lại cho em được không?
This?
Vâng.
Ok, cái này thì nó thuộc về cái vấn đề là về mặt là các bạn hình dung, các bạn vẫn hay nói là một hệ trong tự nhiên thì năng lượng của nó thế nào? Năng lượng của hệ muốn có trạng thái, có xu hướng là năng lượng thế nào?
Thấp nhất.
Năng lượng thấp nhất. Trong trường hợp này thì các bạn hình dung ra 3D, 4 và 4F, 3D và 4F nó có năng lượng gần như là xấp xỉ nhau. Các bạn hình dung không nào? Nó có năng lượng là gần như là xấp xỉ nhau. Chính vì thế mà thực ra là cái việc chiếm các cái vị trí này nó gọi là nó mang tính rất là tương đối. Có thể điện tử nó sẽ nhảy từ chỗ này sang chỗ kia, nghĩa là nhảy từ một cái mức là 3D hay là khác là orbital 3D sang orbital 4S là chuyện rất là đương nhiên vì nó rất gần nhau về mặt năng lượng. Tuy nhiên là khi mà các bạn có cấu hình đầy, ví dụ như trong trường hợp này bạn có 4F là cấu hình đầy, 4F, các bạn có là 3D, trong trường hợp này là các bạn có 3D phải là 10 mới đầy, 4F thì phải là, trong trường này 4F trong phải 4F nhé, cô xin lỗi, cô lại viết thành 4F. 4S2 của nó thì là cấu hình đầy. Thế thì thông thường nó sẽ, nghĩa là nó về mặt năng lượng ấy, thì nó sẽ ưu tiên là lấp đầy 4S để cho nó cấu hình đầy trước. Tuy nhiên là trong cái trường hợp này thì cái 3D 3D, nếu như trong trường hợp này 3D mà lấp 3D4 hay là 3D lấp 3D5 thì cái điều đặc biệt ở đây nó xảy ra đó là nếu nó lấp 3D5 thì cái cấu hình năng lượng này hay nói khác là các cái vị trí để mà lấp điện tử này nó sẽ cho cái hệ là có năng lượng thấp nhất. Bây giờ các bạn sẽ quan tâm đến vấn đề là năng lượng thôi. Năng lượng nó có năng lượng thấp nhất. Đó, thì nó ưu tiên 3D5. Thực tế ra không phải là nó không thể có 3D4, 4S2, 4S2 rồi 4F2 chỗ này cô viết nó đang hơi bị nhầm. Thực tế nó không phải là không có, nó cũng có thể có, nhưng cái hệ mà có năng lượng thấp nhất thì nó cho là 3D5 và 4S1 hoặc 3D4, 4S2 cũng được. Tuy nhiên rằng là nó sẽ ưu tiên cái cấu hình 3D5, 4S1 này trước. Đó, đây các bạn nhìn ở đâu đây? 4S và 3D nó nằm ở đây bên này. Đây, nó sẽ là nằm trường hợp của cái nguyên tố này. Đây, 3D, 4S đây các bạn nhìn đây nhé, nó sẽ là cái nguyên tố này. 3D5, 4S1 đây. Đấy, đáng lý chỗ này nó phải là 3D4, 4S2 nhưng nó sẽ nhảy cái chrome này về cái cấu hình 3D5, 4S1. Sau đó nữa đến mangan thì nó lại là 3D5, 4S2. Đó. Các bạn hãy quan tâm đến vấn đề năng lượng của hệ sẽ là năng lượng tối thiểu. Được chưa nào? Đợi cô một tí nhé. Các bạn đừng nghĩ cái gì quá sâu xa về những cái hệ, về những cái chỗ này. Cái chỗ này là các bạn cứ luôn luôn nhớ cho cô, đó là về mặt năng lượng là nó phải minimum, thế thôi. Còn tại sao nó lại như thế? Tại sao lại như thế thì nó là về mặt cấu hình, nó là cái người ta sẽ, nghĩa là để mà giải thích được thì nó sẽ rất khó để các bạn có thể giải thích được, vì trong trường hợp này là nó còn có cái hiện tượng là các cái giữa các orbital nó có các cái sự lai hóa tương tác lẫn nhau nữa. Đồng ý chưa nào? Okay. Any question here? So we move to another section. Spin orbit coupling. So in the many electron atom, you have the similar models for spin orbit coupling, and you will have L and S and J quantum number. For this, you restate Hans rule. In this, the orbital will arrange in the orbital for the maximum quantum number S and the maximum quantum number L in the total atom. And the test is the values of J. J will have L minus S with the number of electrons smaller than the a half of the total electron in the subcell. And J equal to L plus S if the number of electrons larger than a half electron in the total subcell. Yes, a half of total electron in the subcell. And J equal to S if N equal to N divided by 2. For example, you can consider, for example, 5D, for example, or 3D. 3D is okay. So if you only have three electrons in 3D, so you can see that 3 electrons in this case will occupy, yes, this, 2, 1, 0, -1, -2. And the first, you can see that you have 3 electrons in the D subcell. So you have 3 electrons will occupy 3 different orbitals. And with the spin up like this. And this arrangement will give 2 conditions for S max and L max. The first is S max. In this case, it's all upspin. So you have S maximum equal to a half plus a half plus a half, and you have 3.5. And the second L max. In this case, you can see L and this equal to 2, 1, and 0. So in this case, L max equal to 2 plus 1 plus 0 and equal to 3 here. And 3. And 3. It is because in this case, N, the maximum number of electrons in this case equal to 10. 10 electrons is the maximum. In this case, you only have 3. So N in this case smaller than N divided by 2. So in this case, J equal to L plus S minus S, I'm sorry. So equal to 3 minus 3.5 and equal to 3/2. Yes, and that is the ground state. Ground state. Yes, the ground state of the atom that have 3, or the atom or ion that has the subcell 3D. In this case, you can see 3D in this. Yes, 3D3. 3D3 in this case is vanadium. It's a 3D3 and 4S2. Yes. Vanadium. Vanadium in this case corresponding to this example. Correspond to this example. Vanadium. 3D3. Yes. Yes, from this you will have the spectroscopic notation of this subcell. Of this subcell, you will have L equal to 3 and S equal to this and J equal to this. Yes. This is the way you calculate the S, L, and J quantum number of the ground state atom. So from 3 values of L, S, and J, you can calculate the magnetic momentum of the atom. And the magnetic momentum of the atom, you can use the formula for hydrogen atom here. It's similar with hydrogen atom. It's the same with hydrogen atom. And in this case, you need to remember that Gj equal to 1 plus L, J plus 1, S plus 1, L plus 1, and 2J plus 1. In this, you can remember that J in this case is quantum number. Quantum number, and you can calculate the quantum number from the configuration and use the Hans rule. The Hans rule, you can calculate S and L and J. Yes, and from this you can, if you know the configuration of electron, you can calculate the Landau factor here. The Landau factor here, and from this you can calculate the effective magnetic momentum of atom. Yes. And from this, you can calculate this. Yes, they are all the quantum number. And from this, you can also see that because mu F in this case have mu F in this case have this formula. And from this, the G component of effective magnetic momentum, similar with hydrogen atom, you can see it has the 2J plus 1 different values of mu G, different value of mu G. And of course, in the magnetic field, the mu G in magnetic field with different or 2G plus 1 different value, it will be split into 2J plus 1 different energy level like this. Like this, you can see here. The first, the second, the third, and the fourth, for example, here with J equal to 3 divided by 2. Yes, yes, you can see. The splitting of energy into 2J plus 1 in the magnetic field. Yes, yes. And of course, when you place the atom in the magnetic field, the energy will be split into 2J plus 1. Yes, you remember this? Yes, and in order to consider the transition of electron between these energy level, you need to consider the selection rule. The selection rule, another selection rule for the many electron atom. This is a selection rule for many electron atom. Yes, with the accounting of the spin orbit coupling or the magnetic model or the magnetic model of atom can be applied. In this case, you need to have the J equal to equal L plus S. Yes, you need to have this, and it is the spin orbit coupling model. And when you use spin orbit coupling model in this, you need to apply the selection rules for the transition. Yes, and the selection rule for the transition in the many electron atom here can be stated by this, by 4, 1, 2, 3, and 4 points, different points here. Yes, you already have one selection rule for hydrogen atom. Selection rule. It's only, do you remember the selection rule for the hydrogen atom you already stated? Who can remember? The selection rule for hydrogen atom? Tiến Bình. How many points?
The 2 points in the selection rule. That
the first
ML had to change.
ML change
0 or 1. Only change 0 or 1.
0 minus and plus 1.
Yes.
Yes. Second.
L is change 1.
1. Plus or minus 1 depends on the absorption or emission. Yes. Okay. And then you have another selection rules for the spin orbit coupling in many electron atoms. You have 4 points here, and you need to remember delta J 0 plus minus 1, delta L 0 plus minus 1, delta S equal to 0, delta MJ. Similar with ML here, it is MJ here equal to 0 plus or minus 1. You need to remember. However, there are some special cases. You have 2 special cases here. The transition between J0 is not allowed. This transition is forbidden. This transition is forbidden. This. And another forbidden transition is the from J equal to 0, Mj equal to 0 to one another state that have delta or delta Mj equal to 0 is not allowed. With this state, there is not a transition where delta Mj equal to 0. Yes, it is one forbidden transition, one another. Yes, in the transition, there's only one electron. So delta L must different from 0. Delta L only equal to 0 if you have the transition that's involves from 2 or more than 2 electrons each one in the transition. However, in the normal transition, you need to remember that delta L only equal to plus or minus 1. It's similar with the condition below. So in this case, you remember the transition is usually equal to plus or minus 1. Yes, and in this